Hello everyone, my name is Giancarlo Mejia. I'm a senior in mechanical engineering and I'm with group number 3, and this week I was the reporter for the bomb calorimeter experiment. So just a very brief introduction to the experiment. The bomb calorimeter is used to measure the heat liberated by combustion of a fuel sample, as well as to analyze the resulting products. The most important thing to note here is that this is a constant volume process. This simply means that there won't be any work done to the system. We'll go into detail about how we can derive the equations from the first law later on in the presentation, but just remember, constant volume, no work. So the goals of the experiment are to become familiar with the physical principles and the analysis associated with the bomb calorimeter, as well as to determine the thermal heat capacitance of the calorimeter itself. Thermal heat capacitance can be defined as the amount of energy to change the temperature by 1 degree Celsius per unit mass, as well as determine the gross heat of combustion for the fuel samples provided. So just a brief explanation of the experimental apparatus. We do have an overall picture of the setup on the left and a more in-depth picture of the bomb itself on the right. I do have the labels here, but probably one of the more important things to note is the stirring motor. The stirring motor is specifically used to keep the water uniform around the bomb, such that we can take accurate measurements of the temperature of the water using the thermocouple. The electrodes provide the electricity to the fuel sample that's being held in the crucible, and then the ignition wire as well. All of this stuff is self-explanatory and also explained in the group lead presentation the week before, so I won't go too much into detail there. But remember, stirring motor, uniform temperature for the water. So some equations that we'll be using here are the first law. Remember I mentioned constant volume, which means no work, which means we can simplify and rearrange to get the internal energy equal to the heat added to the system. We end up with Q equals mass times CV, which is the specific heat capacity at, the specific heat at constant volume, as well as times the change in temperature of the experiment. Now, if we take the calorimeter as the thermodynamic system, which is everything but the fuel consumed, we actually get an equation for the thermal capacitance of the calorimeter is equal to the heat generated by the fuel and the wire together, divided by the change in temperature of the system. On the right here, we have, well, since we have to include the heat of the wire on the right, we have the equation to determine that. This is provided by the chart for the ignition wire. So I do have to mention briefly that the data that we took after running the experiment twice for the benzoic acid was not accurate, as we can tell from the chart, but we were allowed to use a different group's data, and their data for the benzoic acid, which is group 2, looks like this. Pretty simple stuff. We have about a 3 degree change in temperature over 700 seconds. The purposes of taking the graph are just to determine that change in temperature. And here's for the unknown fuel source. The 2 fuel sources that I hadn't mentioned before are going to be benzoic acid and manganese. Now let's get to the good stuff, the sample calculations. So for the benzoic acid, we were given the heat of combustion, but if you notice, it's a per unit mass, which means it's equal to lowercase q. And the right side of the equation becomes CV equals dt. To get capital Q, which is not per unit mass, we have to multiply by the amount of mass of the benzoic acid that we use as a fuel sample, which is 1.1 grams or 0.001 kilograms. And we end up with a heat of 29.11 kilojoules for the benzoic acid after combustion. Now, we set that to the left, and we move mass to the right, combine it with CV to get our thermal capacitance, and we actually end up, we can actually use the equation mentioned previously, and we end up with a thermal capacitance of the benzoic acid as 9.36. We do a similar process for the wire, and we end up with a thermal capacitance of 0.02289. When we combine the two, we have the thermal capacitance of the calorimeter, which is 9.38 kilojoules per degree Celsius. Per degree Celsius, it's going to mean, or rather, this property is an extensive property, which means that it's dependent on mass. I'll explain that a little bit further, but probably explains why we use 2 liters of water, maybe to keep the calculation simpler. Now for the sample calculation for the unknown fuel source, we have to find the heating value. Now if we assume that the calorimeter thermal capacitance is constant, we can use that equation, or rather that value in our calculations here. So we do the process again, right? We find the heat of the wire, we add it to the heat of the unknown source. We know that thermal capacitance is constant, and we know the temperature change. Therefore, we can find the total heat of the unknown fuel source. And the heating value of the fuel source is found by dividing by the total mass of the fuel, which we end up with a 15.78 megajoules per kilogram. Now, some comparisons. The estimated calorimeter value was 9.76 because we assumed 2 liters of water and 3 kilograms of, or rather 2 kilograms of water and 3 kilograms of steel. It ended up being just slightly higher than our calculated value, about 9.7% difference. The amount of wire consumed for the benzoic acid is greater, meaning it generated a higher heat. The change in temperature, which is reflected by that, is greater for the benzoic acid than the unknown source, and the overall heating value is about twice as more than the unknown source. Some common fuels encountered are gasoline, propane, ethanol. Their values are here. And this is important because it lets us know that the higher the heating value, the less fuel you actually have to consume, therefore more energy per fuel. Possible uncertainty, depressurizing of the bomb, wire not intact, and such things. And yeah, these are my references.